Hello class, welcome to the first episode of The Professor. Today we will be learning about reasoning with uncertainty, and to start this lesson off, let's start with a quote by Pierre-Simon de Laplace. He said that the most important questions of life are, for the most part, really only problems of probability. True enough, when we ask ourselves, what are the chances that I become successful in my field, or what are the probabilities of me becoming a millionaire? Or maybe if I date this girl, what are the chances or the probabilities that we end up together forever? So maybe if we start learning more about probabilities, we get to tip the scales and move the odds to always go in our favor. So, for our outline, we will be discussing about probability, independence, belief networks, probabilistic interference, stochastic simulation, and sequential probability models. But for this video, we'll be focusing on probability and independence first. To start off, according to the book Foundations of Computational Agents, intelligent agents in real environments are inevitably forced to make decisions based on incomplete information. Even when an agent sends out to the world to find out more information, it rarely finds out the exact state of the world. A doctor doesn't exactly know the state of its patient. It can only know so much about the symptoms and whatnot, but does not really exactly know what's happening in the inside. Or maybe on my part, I'm not quite sure if you'll be able to understand the things I'm going to say, because I don't really know what's going on through your brains. But I will find solace in the probability that you will understand the things that I'm saying based from your previous experiences and your backgrounds. Considering this dilemma, an autonomous car only knows that there are two people ahead. Now these two people have the probabilities of crossing the street or just walking straight, so that when the car moves at a constant speed, it won't hit them. But to make a good decision, an agent cannot simply assume that none of these people will cross the street and speed up under the assumption that it won't hit them. It has to consider multiple hypotheses before making any decisions. So what do you think will the autonomous car do? Calculus is just the probability is just basically the calculus of gambling. When we gamble, we make decisions and we do not know the outcomes, therefore we take risks, right? But it still begs the question, how does an intelligent agent choose which risks to take? To somehow enlighten us on this question, let's take this example. For example, Rose decided to roll a die, so it has 6 probabilities, right? 1, 2, 3, 4, 5, and 6. And the outcome was 5. And then Rose made 3 other people guess the outcome. Mark, Marlon, and Marieto. He told Mark that the outcome was 5. And so Mark's guess was 5. He told Marlon that the outcome was an odd number. So Marlon guessed that the outcome would be 3. But Rose did not tell Marieto any clue or any idea or any knowledge about the outcome. And so Marieto guessed 6. Now if you come to think about it, the chance of Mark being right is 100% because Rose already told him the outcome. So Mark gets 100% probability of getting the correct answer. However, Marlon, who knew that the outcome was odd, only had 3 choices. He could either choose 1, 3, or 5. Therefore, Marlon had a 33% probability of being right. But for Marieto, he did not know any information about what the outcome would be. So he only gets 16.67% probability that he will get the correct answer. In Bayesian probability, we are assuming that the uncertainty is epistemological rather than ontological. Epistemological means that an agent's beliefs of the world is basing from an agent's knowledge or prior information of what the world looks like rather than of what the world actually is. So let's take, for example, we have a plantita from Mandaue and a plantita from Busay. And what is the probability that both of these plantitas get a successful blooming of flowers and plants? We do not just simply say that a plantita from Busay will have a greater chance of success because that's just how the world works. That's just it. That's just the way it is. But rather, we say that the plantita from Busay will highly succeed because it knows more about plants and flowers. It knows how to grow them, how they behave, or whatnot. So, the question is, how do we apply this to our intelligent agents? And how do we apply it when we want to build one? So the key would be, the more information we could feed the agent, the better decisions it could make, and the more rational and relevant decisions it will take. So now let's proceed with the semantics of probability. So the probability of theory is built on worlds and variables. We can think of the worlds as object representations of the world, and as the variables as the features of this object. Same analogy with class and data members in object-oriented programming. Variables will be written starting with an uppercase letter, and every variable has a domain. A domain represents the set of values that a variable can contain. So for example, we have a world mark that could have a variable handsome, and it could have a domain of true or false. Primitive proposition, on the other hand, is an assignment of a value to a variable, or an inequality between variables and values, or between variables. So for example, in the rolling the die scenario in the previous discussion, we could create a primitive proposition where we say that the outcome is equal to 5. That's our primitive proposition. And with this primitive proposition, we get a probability of 16.67%. Probability measure is calculated through the summation of W, where W is equal to 1, and W is an element of omega, and where omega is the set of all possible worlds. So in simple terms, we just count all the worlds with a probability of 1, we add them together, and we get the probability measure. To further understand this formula, let's try to extend the definition of P. So let's say, for example, that P alpha, or the proposition of alpha, is equal to the summation of all the propositions, of all the worlds where the proposition is true in W. So let's take, for example, this world. This space has 10 worlds, if we count it. And since it has 10 worlds, each of the world has a probability of 0.1, or 10%, because 1 divided by 10 is 0.1. We also have variables filled, which has a domain of true or false, and shape circle, triangle, or star. Now, if we have a proposition alpha where we say shape is equal to circle, then if we look through the formula, shape is equal to circle is true, so we add 0.1, plus shape is equal to true, shape of circle is equal to true, another plus 1, shape of circle is equal to true, plus 1, shape of circle equal to 2, shape is equal to circle, so another plus 1, plus 0.1, and another shape is equal to circle is true. So the proposition alpha is now 0.5, because when we say this shape is equal to circle, it's false, so it doesn't add to the summation. So in the end, we get the value proposition alpha is equal to 0.5, or in other words, there's a 50% probability that in this world we get a circle shape. So now we go to the axioms for probability. Axiom is somehow a general rule or a golden rule in probability. Axiom number 1 states that a probability could only either be greater or equal to 0 and less than or equal to 1. Probability can never be a negative number. Axiom number 2 states that if all the worlds in possible worlds are true, it should always sum up to 1. That's why in the previous slide, these are all the possible worlds, each of them containing 0.1 probability, and when we add all the probabilities of these possible worlds, we get 1. So that's a proof of the second axiom. And for the third axiom, if proposition A and proposition B are contradictory propositions meaning that they can never happen at the same time. For example, if we play a deck of cards, would it be possible that if we pick one card from the deck, we get a king of hearts and a king of diamonds? We could only get either of one, right? So to be able to get the probability of getting a king of hearts or a king of diamonds, we'd have to add their probabilities. So the probability of getting a king of hearts is 1 over 52 because there are 52 cards in the deck. And the probability of getting a king of diamonds is 1 out of 52. We add them both together, so we get that the probability of getting a king of hearts or a king of diamonds is 2 out of 52. Conditional probability. The probability that event A occurs given that event B has occurred is called conditional probability. The conditional probability of event A given event B is denoted by the symbol P, event A, probability of event A given B. So for example, we have an IT graduate who would pursue a master's degree given that they were able to finish college. Another example would be if we have a jar filled with 5 black marbles and 5 white marbles, and we are asked to pick 2 marbles from the jar. What is the probability that we get 1 black marble given that the other marble that we get is white? So there's more of like dependency of events. On one event affects the probability of the other. Well, independence on the other hand is quite the opposite. If the occurrence of event A changes the probability of event B, then events A and B are dependent. On the other hand, if the occurrence of event A does not change the probability of event B, then events A and B are independent. For example, when we toss a coin, the probability of it being heads or tails is no way affected by what time of the day it is, right? Or the probability of Trump losing the US elections is not in any way affected by my personal opinion because I cannot vote in their elections, let alone am I a US citizen. So in summary, these are just very important notes to remember, which we'll be using in the future discussions. 2 events are mutually exclusive or disjoint if they cannot occur at the same time. The probability that event A occurs given that event B has occurred is called a conditional probability and is given by the symbol probability of A given B. The complement of an event is the event not occurring. The probability that event A will not occur is denoted by probability of A complement. One example of this is if we toss a coin and if the probability that we get a heads is 0.30, then of course the probability that we get tails is 0.70. Next, the probability that events A and B both occur is the probability of the intersection of A and B. The probability of the intersection of events A and B is denoted by A intersects B. And if A and B are mutually exclusive, then the intersection is 0. Because again, when we say that probabilities are mutually exclusive, meaning they can't happen at the same time. Next, the probability that events A and B occur is the probability of the union of A and B. The probability of the union of events A and B is denoted by A union B. Lastly, if the occurrence of event A changes the probability of event B, then events A and B are dependent to each other. On the other hand, if the occurrence of event A does not change the probability of event B, then events A and B are called independent. So this is it for the first video. For the second video, we'll be talking about Bayesian networks and Bayesian probabilities in depth. Thank you.